In this video, we are going to cover nonlinear transformations. These transformations are very useful because they allow us to address violations of the linearity assumption. Let's look at some data. Here on the x-axis, we have the GDP per capita at purchasing power parity. And on the y-axis, we have life expectancy. We can see some relation, but it's clearly nonlinear. If we fit a regression, you can see that the line of best fit is not really good. You have a lot of observation below the line around 0, then it gets all above the line, and then after 30,000, you get all the points below the lines again. So clearly there is a violation of linearity. What can we do about that? We can use nonlinear transformations. These transformations are simply some mathematical functions that are nonlinear and that we apply to a variable to get a new variable. These transformations are usually applied until we get some linear relationship between our new variables. You can transform the explanatory variable x or the outcome y or both. We will just try to find the correct function. The correct function will be the one that gives us some linear relationship. But once we find these functions, we have to be careful because it alters both the relationship between x and y and the interpretation. So it will change everything. The estimates, the p-values, the r-squared, the standard errors, the confidence interval, and other statistics. The first transformation is the natural logarithm. When applied to x, it enforces decreasing marginal returns. What it means is that when x is small, a small change will have a large effect on the predicted y. However, when x gets larger, the effect of a change in x on our prediction is smaller and smaller. What is good about the natural logarithm is that it doesn't require any additional coefficient. The other good thing is that you can interpret it as a percent change that we'll see later. The problem is that it doesn't work with x less or equal to 0 because a log of 0 is minus infinity. It also only works when y hat increases or decreases with x, but not both. It cannot increase on some x and decrease on some other x's. So here is the same data, but instead of using the GDP per capita, we have used the log of the GDP per capita. You can see now that the relationship looks a lot more linear. So our line of best fit looks like it's actually a good fit. And we have here the estimated coefficient. The intercept is minus 2.92 and the slope is plus 8.035. How to interpret this model? We can see that the model doesn't have any transformation applied to y, so it's linear in y, but we have a log applied to x, so we call this model a linear log model. If we want to know the effect of an incremental change in x on our predicted value for y, we can take the derivative of y hat with respect to x. In that case, the alpha coefficient disappears, and then we have the beta coefficient times the derivative of log x. The derivative of log x is 1 over x. How to interpret that? A small change in x is associated with beta hat times 1 over x times this change in y hat. So you see that we need to know what x is to interpret this change, but we can do something else. We can take the small change in x, so the delta x, and put it on the other side of the equation. And now we have the small change in y is equal to beta hat times the small change in x over x. This part here can be interpreted in a way that is a percentage change. For instance, if the change is 1 but x is already 100, so it goes from 100 to 101, then we have 1 over 100, it's a 1% change in x. So the interpretation will be that the small change in y is beta time the percentage change in x. Let's apply this reasoning to our case of life expectancy with respect to GDP. So here the coefficient of interest is 8.035. Be careful, a 1% change in x is a 0.01 change in x. So in that case, we have to take 0.01 times the slope. So we get approximately 0.08. Our interpretation will be, on average, an increase of GDP by 1%, so that's 0.01, is associated with an increase in life expectancy by 0.08 years, everything else being equal. Be careful, students often make the mistake of just putting the coefficient there, so they write 8.035. If you forget to divide by 100, you are going to have the wrong interpretation. Now, let's talk about calculating elasticities. An elasticity is the expected percentage change in y hat for a percentage change in x. So we have percentage both on the y side and on the x side. That's convenient because now we have something that doesn't use unit. It's a unitless comparison across the variable. To get that, we need to apply the log transform both on the y side and on the x side. And then the beta hat is the elasticity. So the equation becomes log of y hat equals alpha hat plus beta hat log of x hat. So put both the log on y and on x, and we have a model called a log-log model. The log y will become a change of y hat in percent, and the log x will become a change of x in percent. Something interesting is that since we both have a percentage change on the y side and on the x side, both are in terms of 0.01 change, and so it cancels out. So the interpretation would be, on average, an increase of x by 1% is associated with an increase in our predicted y by beta hat percent, everything else being equal. We don't have to multiply or divide beta hat by 100. Now that we have seen the log transformation, we can move to the square transformations. The square transformation is when we apply a square to the x variable. And in that case, we both have x and x squared in our equation. It allows for a u or an inverted u relationship between x and y. And depending on the beta coefficient, you can have different shapes of u or inverted u relationships. It can be thought of as x interacting with itself. So it's like beta 1 x1, beta 2 x1 times x1. So it is good that it can take many shapes and that it works with all kinds of x and y values. However, it requires two parameters. We need both a beta 1 x1 and a beta 2 x1 squared. How to interpret incremental changes with this kind of models? Well, how does y, the expected y, reacts to a small change in x? In that case, we just take the derivative of y hat with respect to x, and the alpha coefficient disappears. There is no x here. And then we have beta 1 hat times x. The derivative is just beta 1 hat. And then we have beta 2 hat times x squared. The derivative is beta 2 hat times 2x. The derivative of x squared is 2x, so we just put 2x's here. The interpretation is then a small change in x is associated with beta 1 hat plus 2 beta 2 hats times x times this change in y hat. You see that the incremental change to be calculated requires us to know the value of x. We have to set x to get this change. For instance, we can ask for the incremental effect of x on our predicted y at x equals 1.5. Let's say we have the estimated coefficient of alpha hat equals 0, beta 1 hat equals 1, and beta 2 hats equal 2. If we plug this in our equation, we find that we have a total change of 7. So we would say, on average, when x equals 1.5, so we have to say where we are on the x-axis, an increase of x by 1 unit is associated with an approximate increase in y hat by 7 units. Note that I use approximate here. Why? Because we are following the red line on the graph. We are not following the curved line. And of course, we conclude by saying everything else being equal. You have to be careful here. This interpretation is valid for small changes in x, so small incremental changes. Indeed, we are taking the derivative, so we are using the red line on the graph. We are not using the actual model, which is a curved line. So for the derivative at x equals 1.5, the red line on the graph, we found that we have an approximate increase in y hat by 7 units when x increases by 1 unit. So on the graph, it's following the red line, and the approximate change in y hat is the value for y at x equals 1.5 and the value for y hat at x equals 2.5 on the red line. You can see that the actual change for our model is actually larger. If we go further than that, you see that the red line and the curved line grow further and further apart. So the approximation will get worse and worse. So what should we do instead? Well, the best is to compute the y hat, the expected y, at both x equals 1.5 and 2.5 using the whole model instead of using the derivative. So for x equals 1.5, we find that y1 is equal to 7. And for x equals 2.5, we find that y2, the expected y2, is 15. So in that case, the expected change in y hat when x goes from 1.5 to 2.5 is 8 and not the approximate 7 we found before.